Okay, so second attempt. Good afternoon, everyone. So my name is Elisa Bernardini, and I'm here on behalf of the director of our institute, Professor Flavio Seno, who cannot be here today because of too many conflicting overcommitments. So I warmly welcome you to the new season of our Colloquia program. And this program is specifically designed for students, bachelor, master, PhD, and all of us. So also, let's say, seniors, because they are thought to be didactical introduction to specific selected topics of research. Meaning, of course, that we cannot cover everything. Every year we try to choose different topics, but with the purpose of providing some new highlights on results or discussions on topics that are of wide interest. So this year's program, just for giving you an idea, includes topics that range from collective communication in complex systems, or formation and evolution of galaxies, climate changes, gravitational waves, and quantum technologies as an appetizer. I warmly welcome everybody to attend them because it's an opportunity for all of us for getting educated about what's going on in a field of research or studies which is not necessarily what we are confronted with every day. And I also warmly welcome you to ask questions or to be interactive in this, and I hope that you enjoy that. Thank you very much.
So, thank you, Elisa, for the introduction. So it is my great pleasure to introduce to you today's speaker, Professor Giovanni Isella from Politecnico of Milano. Giovanni got his PhD in physics from Politecnico of Milano, and afterwards went to the ETH, the prestigious institute in Zurich, to spend his postdoc. Then he came back to Politecnico, where he is now full professor of experimental physics. He's since 2007, he's the leader of the silicon germanium epitaxial team at the laboratory for nanostructures and spintronics of the Politecnico of Milano. And his research interests are focused on the epitaxial growth and applications of silicon germanium heterostructures and devices. And specifically in today's colloquium, he will discuss how it is possible to tailor the energy band gap of silicon and germanium heterostructures by combining a variety of techniques, experimental techniques, which include epitaxial growth, substrate patterning, and pulsed laser melting. And in this way, it is possible to realize novel smart materials which can find a broad range of applications spanning from going from optoelectronics to possibly quantum computers. And we are all looking forward to your presentation.
So, thank you. So thank you first of all, for the invitation, then for a very nice introduction. It's really an honor for me to be here in this institution, which has a history which is basically as long as modern physics, because the entitlement to Galileo is not made by chance. So it's really a pleasure and an honor. What I would like to tell you this afternoon is how actually over the past 20 years I've been working on mixing different semiconductors to develop new materials which can be tailored to different applications. So if we look at the technological evolution of humanity in a glance, 10,000 years ago, people were struggling to make tools for agriculture, and then let's say essentially the two industrial revolution came, and for sure we can say that our lives, our daily lives, have been transformed by the application of semiconductors, because essentially they are now everywhere in our activity. So the first thing that came to our mind when we talk about semiconductors is digital electronics, so computers and telecommunications. So it's very hard. I mean, every time we pay something or we take a medical exam, we rely on this technology. They're also relevant for solar cells. This is the case of, let's say, Earth terrestrial solar panels, but also all the satellites are essentially powered by solar cells. So also all the things we can do with satellites, communication, observing the Earth, are empowered by semiconductors. Another relevant application is the one for developing lasers and LEDs, so which are used in telecommunication, but also in many physical experiments. One of the Nobel this year was awarded to 3 scientists who actually developed attosecond laser sources. Silicon has also, or let's say semiconductor, has also relevant mechanical features. So microelectromechanical systems are in our mobile phone, but again, they can also be used in science. For example, you can measure gravity with these tools. This is a not updated map of a network of fibers which runs all around the world to support the internet. So 99% of the information traveling on the internet is basically based on this network. And every few kilometers, you have a stage where the optical signal is taken, reshaped, and sent out again. And this is, again, electronic and lasers coming in. And also, one of the things I will be talking about today is the possibility that semiconductors give us to see beyond our eye capability. So, for example, with infrared light, we can see through fog. So this is exactly the same scene. And here we can see that there is a person behind that maybe needs some help. And this is, again, a visible and an infrared image of just fields. And you can basically tell if they are in a good or a bad shape, the chlorophyll content in this area. And all this is, say, empowered by semiconductors. So if we look at this subsection of a periodic table, which is centered around group 4, basically by combining these elements, we obtain not 100%, but a lot of a semiconductor we commonly use. And the reason why this material are semiconductor is relatively simple. So if we take group 4 as a prototypical case, we see that the atomic shell is formed by 2 electrons in the S states, which is field, and 2 electrons in the P states. So we still have 4 electrons that could actually fit in this atomic level. And so if we take this tetragonal coordination, where we have 1 atom in the middle and 4 dangling bonds around, if we coordinate this central atom with our 4 atoms, we will actually form a covalent bond while we fill this atomic shell. And so this is exactly what happens in semiconductors. So for example, in silicon, what happens is that this, say, Lego block given by this tetragonal coordination is assembled in this diamond shape. In the case of 3,5 material, a lot of them crystallize in this zinc blende structure. So you see that now the average is still S2P2 as an orbital configuration. And so now it will be essentially similar to the diamond structure, but now we have 2 different atoms, a central one, which can be group 5, and the other 4, which are group 3. And also many 2,6 materials follow this recrystallization. And we have several materials. The more relevant ones are those involving nitrogen, which is very electronegative, which form this Wurtzite structure where you can still recognize this tetragonal coordination for field. So basically, if you take this group 4 element or you mix up 3,5 or 2,6 material, with a very high probability, you end up with a semiconductor. And so this is a very popular chart that you can find in many textbooks, which is kind of our map that we will use today, where we see the band gap. We will see later what exactly it is, but it's essentially the energy difference that the semiconductor can take or release, and the difference lattice constant. And here, these different compounds are color-coded. So we have in blue the nitrides, like gallium nitride or indium nitride. These are materials extremely relevant for example, LED, so high-energy LED, which are then used to have a white light. And nowadays, gallium nitride is also important for power electronics, which is used in the automotive industry, for example. 3,5 material are essentially used for making lasers for telecommunication or in general also spectroscopy. 2,6 are emerging as material again for making light sources. Actually, this year, Nobel Prize for Chemistry was awarded for the synthesis of colloidal quantum dots. Essentially, these colloidal quantum dots are formed using cadmium selenide or cadmium sulfide in most cases. So again, we find also semiconductor in chemistry. And the material class we will talk about today is group 4. So we have carbon in the diamond phase, which is not actually a semiconductor. It has a very large band gap. And then we have silicon, which is at the base of our telecommunication revolution, as we said. Germanium, which is a step below. And here I've added tin, which is actually in a, say, metallic phase, a semi-metal. So it has a negative band gap in this plot. But we will see that we can mix it with germanium to make it a semiconductor. So which are the main features of a semiconductor? There are actually two ways that can be used to represent how the energy levels are filled in a semiconductor. We have the band diagram, which is essentially used by electronic engineers, where we have space on one axis and energy on the other. And in these diagrams, we have a forbidden energy gap, which separates the valence band, which is essentially filled with electrons, and the conduction band, which is typically empty. Let's say at low temperature, you would get this. If you increase the temperature, what you get is that some electrons are promoted in this conduction band, and so you will have conduction here, because you will have free states where the electron can travel, but you will also leave some empty levels here, which are called holes, so, and behaves like, under any effect, as positive charges. So this, say, bipolar nature of conduction is one of the main characteristics of semiconductors. So in metal, you typically have conduction, negative conduction from electron. I think beryllium is one example of a simple element where conduction is made by holes. But in semiconductor, you can have both things at the same time in the same material. And the other way we use in physics to represent a semiconductor is a band structure. So where we have, again, energy on the y-axis, and on the, say, x-axis, we have the crystal momentum, which is essentially the momentum that a particle has in a periodic system like a crystal. So here we find, again, the energy gap. But this plot gives more information because, for example, we see that we can have more gaps, the one from this central point to here, which is called indirect, and the one from this point to the upper point, which is called direct. And for example, we will see that to absorb light, this transition is more efficient than this one. This band structure, we will see later some more realistic representation, can very often be approximated using this parabolic behavior. So we fit a parabola around the minima or maxima of the state, and this parabola will describe the motion of a particle with a mass which is no longer the electron mass, but the effective mass, where essentially this number here, actually in more complicated vision is a tensor, but say this number is actually condensing all the complexity of the band structure. So for example, we can define two broad cases where we have a heavy effective mass, which means that we have a very large curvature here, or a light effective mass when this is a smaller curvature. And for example, the effective mass enters in determining the carrier mobility. Yes, there is a bit missing. So how fast an electron or a hole move in a semiconductor. And this is ultimately one of the parameters telling us how fast a transistor can behave. So if the carriers are slow, I will never reach a transistor with a gigahertz operation. And so typically, if the effective mass is lighter, I will have a faster carrier and a faster device. Another let's say, class of phenomena where the effective mass enters is in determining the carrier density, or the so-called density of states. And here we have this dependence from the effective mass. So let's suppose that we have two bands with the Fermi level separating the occupied state and unoccupied state here. I mean, basically, the number of carriers I will have is proportional to the area of these two figures. So you can understand that with a heavier mass, I would get more carrier than with a lighter mass. And finally, we will discuss about quantum confinement in heterostructure. So we can take as an example a simple quantum well. This is a well-known formula of an infinite barrier quantum well, where A is the dimension of a quantum well. Here again, the effective mass pops up. And essentially what will happen is that if I have a heavy mass, I will have more level, which are more finely spaced, as compared to the light mass case, where I will have fewer level, which are more separated in energy. We will see at the end of our talk that this, for example, is important to making qubits and isolating an electron or an hole in a quantum well. So to conclude this introductory part on semiconductors, I have listed here, three things which are unique of this world that you cannot do with a metal or with an insulator. So the first thing, I partially mentioned it. So you can actually have both type of conduction, so p-type conduction or n-type conduction by doping your material. And this is at the base of all the electronics. So all electronic devices to a different level of complexity contain junction between p and n doping. So this is the case of a transistor. And so here you see that you exploit this p-n junction 2 times. The other characteristic of a semiconductor is that can emit or absorb light very efficiently, especially if it is a direct gap. And we have seen that we can actually tune or choose between different materials with different gaps. So one application for light absorption is, of course, a solar cell. So what you see here is a spectrum of the radiation reaching the Earth from the sun. And you see the part of this radiation, of this energy, which is collected by silicon, for example. So a different semiconductor will cover this area differently and give you a solar cell of different efficiency. So if you want to maximize your efficiency, you also have to, let's say, choose the right semiconductor. Silicon is the right one, also for economical reason, because it's one of the most abundant elements on Earth, and it has a large chemical infrastructure to purify it. And here this is an example that you see in your laboratories every day, the possibility of having lasers, so coherent light with high brilliance, which allows many experiments that would be unthinkable without it. And the other thing which is quite unique of semiconductor is the possibility of making micro and nano fabrication. So the development of a microelectronic industry also led to the development of many tools which allows to fabricate nanostructure essentially on large area. So these days we are talking about 7 nanometer nodes technology for CMOS, and this is done on a dimension of 12-inch, which is basically a large pizza. And also in our lab, we can do microstructuring and build a structure like this, 3-dimensional structure, or make electronic device where we can trap essentially a single electron. So after this, let's say, introduction to the world of semiconductor, we'd like to go more in detail on actually the, let's say, the research that kept me busy over the last 20 years, which is mixing silicon germanium, so the first 2 elements of group 4, and which are the physical properties we can expect and we can obtain from this system. So silicon germanium are one on top of the other in group 4, the group 4 column of the periodic table, so they are very similar from the chemical point of view, so you see the final chemical configuration is the same, is this S2P2 we discussed before. And so by mixing them, we can expect that we can change the band structure and obtain materials which are different from pure silicon or pure germanium. They also have a different lattice parameter, which means that if I grow one on top of the other, I could actually impress some compressive or tensile strain on my system. And those of you already have taken some solid-state physics knows how symmetry is important in a crystal. And so here we are breaking symmetry, at least in one direction. So for example, we can remove degeneracy and engineer the electronic properties of our system. Another thing that I can do with semiconductor, with silicon and germanium, is make a thin, very thin layer of the order of tens of nanometer. And so I can confine electron and holes in a small region where quantum confinement effect pops up, which are not visible, let's say, in bulk material. And another thing that actually we cannot do when we mix silicon and germanium is change the optical properties. So for example, here I have the absorption coefficient of silicon and germanium. So we see the silicon at its band, it's a poor absorber, so the absorption coefficient is very low. So I need to go to quite a short wavelength to have some relevant absorption, and it's essentially transparent below 110, 120, so 1200 nanometers. Instead, germanium is a very strong absorber in the infrared. Actually, this kink in the absorption exactly corresponds to 1550 nanometer, which is a key wavelength in telecommunication. So these two materials, they share the same crystal structure as diamond. So this tetragonal coordination repeated periodically in space. These are the two band structure, where again we have energy and the crystal momentum. So we see that they have quite similar valence band, and the conduction band for the two materials has some differences. So they are both what we call indirect semiconductors, so the minimum energy distance between the valence band and the conduction band is not in the same place in this crystal momentum space. But while silicon has a minimum here in this region, which is called delta minima, germanium has the indirect gap in another region, which is called the L point. And so these are the representation of this minima in the space of crystal momentum. And for the moment, what is important for you to notice is that we have 6 of this equivalent minimum in germanium, so we have a 6-fold degeneracy, while in germanium we have a 4-fold degeneracy, because we are in a different location. If we look at the optical properties, so the absorption coefficient, I've already discussed this a few minutes ago. So basically, the takeaway message is that germanium is a strong infrared absorber, silicon is transparent in the infrared. And if we look at the, let's say, real part of refractive index, we see that germanium has a much larger refractive index than silicon. So for example, in a waveguide, where I need some contrast or refractive index to guide light, I can actually play around with these two materials to have a waveguide made of silicon and germanium. From the structural point of view, silicon germanium is a, let's say, prototypical system. This is a phase diagram. So we have here temperature and composition, in this case, is in silicon, let's say. So we have pure silicon on this side and germanium on the other side. This large yellow area means that any composition of silicon and germanium will give me a perfect crystal, an alloy with a perfect miscibility. So I will form whatever, let's say, combination of silicon and germanium. And the band structure will evolve accordingly. So here, in a bit transparent, you see the original band structure of silicon and germanium. If you mix them up, you see that you have a continuous variation between one of the other. So you can have, let's say, a very gradual variation of properties changing the composition. As far as the lattice parameter is concerned, so germanium has a larger lattice parameter, so this is the variation of lattice parameter of silicon and germanium as a function of composition. So again, we have a continuous behavior, but essentially the lattice parameter of germanium is approximately 4% larger than the one in silicon. So if I try to put, for example, germanium directly on silicon, I can have two main cases which are interested for research and for application. If I grow a very thin layer, and we will see later what thin means, I can have a so-called coherent growth. So the germanium will have to adapt to the substrate, and so it will be compressively strained. So we'll have a strain of 4%, which is not small if you think about having, I don't know, an iron bar which is 1 meter long, and you need to press it by 4 centimeters. You need to apply quite some force, so, and also put some elastic energy in this operation. And so this means that we are actually putting energy in our system, and so this fully strained layer cannot grow infinitely high. At some point, this energy, which I am elastic energy, which I am putting in my system, will have to relax. And this relaxation happens when I go to thick layer and I create some crystal defects. And so in this case, I will have a relaxed silicon layer, and on top of it, a relaxed, plastically relaxed, we say, germanium layer, where essentially I don't have any strain anymore. And these two ingredients are actually relevant for the application that we will see. So what does it mean, thin and thick? Actually, you can make a very simple calculation, which is based on this energy balance between the elastic energy you need to store in your system and the energy required for nucleating defects. And if you make this balance, you obtain this curve, where essentially that tells you, as a function of the germanium content, how thin needs to be your layer to be fully strained. So if it's pure germanium, this would be a few nanometers. If it's 20% silicon germanium, this can be 10 nanometers or more. So these are really, I mean, in any case, the order of magnitude is a few nanometer thickness. So we say that we actually can have a fully strained configuration and a fully relaxed. You can also have situation in between, but this is what we typically want to have in application. So the typical structure of one of the sample we do in our lab is like this. So we start from a silicon substrate most of the time. We can also grow on other substrate, but most of the time of silicon. And then we go a very thick layer, which is a relaxed buffer. Here you see a TM image of a structure like this, where you have all these black lines, which are the crystal defects, dislocation, which are required to release the strain. And on top of this, we can put a strained layer. So the strained layer, we said before, needs to be thin to maintain strain. But then here we have, I mean, different possibilities. So this is a case of a single quantum well. So we can grow 10 nanometer thick quantum well of germanium for electronic or optical application. Or we can also grow a more complicated structure. So this is actually the work of Jacopo Frigerio, one of my collaborators. And essentially, these are quantum wells where two asymmetric quantum wells are coupled together by a very thin layer. So you see all these layers repeating here. And for example, here you can introduce an asymmetry in a material which is typically symmetric, like silicon germanium. So for example, have optical effects that you wouldn't have in the bulk by making this structure. So the main ingredient of whatever you want to do, single quantum well, or let's say coupled asymmetric quantum well, is actually this one. You start from silicon, you grow a relaxed buffer, and then you use a strain on top of this buffer to play around with different quantum and physical properties. So by doing this, you have a zoology of possibility. So depending on which is the composition of the active material of a strain layer and the composition of a relaxed buffer, you have all kinds of band alignment. So you can have situation where you confine electrons inside the well and holes outside, or the opposite, holes inside the well and electron outside, or a situation where you have both electron and holes all together in the same layer. How do we do this experimentally? So I would like just to describe you how basically I earn my daily bread in the lab, what we do exactly from the experimental point of view to obtain this kind of material. So the tool we use for depositing silicon and germanium is a chemical vapor deposition system. It means that the silicon and germanium atoms, before becoming solid and being incorporated on the sample surface, are in a gas phase. So we use, these gases. like silane, which is silicon, and this, again, this tetragonal bond is filled by 3 hydrogen atoms. Germane, which is the same thing. Methane, which we all know is the same carbon with 4 coordinated hydrogen atoms. So everything happens in vacuum. So as many deposition systems, this looks like a chunk of stainless steel, which is pumped out to obtain vacuum. What's happening inside is the following, essentially. So we have a plasma source, which is simply a hot filament which emits electron. These electrons are accelerated in the main chamber, and this plasma is sustained by an argon discharge. So this is very similar to neon tube discharge. It's a DC current. And then we let in our precursor gases, silane, germane, and then we have molecules containing boron and phosphorus for the P and N-type doping. And these molecules are ionized, or in many cases just excited by the impact with the electrons of the plasma. So they become reactive, and when they hit the hot surface of a sample, they basically stick to it in an epitaxial manner. So you maintain the order of the underlying substrate, and you obtain crystalline materials. One of the, say, peculiarities of this technique, which was developed almost more than 20 years ago at ETH Zurich, is that actually you can use the argon plasma to tune over a very wide range the deposition rate, so the rate at which you put materials. So we can go from 5 nanometers per second, which is pretty fast, to much lower, let's say, deposition rate. Why the deposition rate is important? Because essentially, the time a species diffuses on a surface before being incorporated is essentially inversely proportional to the square root of this deposition rate. So if I have a very low deposition rate, it indicates that my silicon atom, for example, can wander for a lot of time over the surface and find the best place to fit. So this would be a crystal site. While if I leave it little time, it will have little time to travel, and so maybe it will end up in a non-crystal site, and for example, in the extreme cases, forming, let's say, amorphous or polycrystalline material, okay? So in some cases, we wanted the deposition to be long. In some other, we wanted to be short to obtain certain effects of keeping the system out of equilibrium. And this tool gives us the possibility of tuning this effect. So one example is here. So we have 2 layers of silicon germanium, 70%. One is deposited at a given rate at a high temperature. So in this case, what happens is that the material travels around and forms this ugly surface, because actually roughening the surface is one of the mechanisms that the system has to release strain. In the other case, we reduce the temperature, but we maintain the rate still high. And so what happens is that we have a much flatter surface with roughness you can find here we go from 10 to 2.5 nanometers. So whatever device you want to do, you would rather prefer a flat interface than something messy like this. And this is essentially controlled by controlling the deposition rate and the temperature of the deposition. So what we typically do in our growth of silicon germanium, we work on these 2 parameters, temperature and deposition rate. And so, for example, if we want to grow a layer like this one, where we essentially increase the germanium content linearly from 0 to 70%, to stick to the case before, at the same time, we reduce the temperature continuously. And we can actually very finely control the composition by this method. Actually, this is data taken here several years ago. Probably Enrico remembers. So this is SIMS analysis of this sample. So we are looking at the tail of this sample. You can see these steps. These are the individual variation of gas flux. So our mass flow controller, the tool that delivers gas to the system, works in steps of 0.1%. and we can actually retrieve them. So this tells us how finely we can control the composition with this method. So this is what I mean, some the experimental part on how we actually produce a material that you will see. And now, for the remaining part of the seminar, I would like to give you some introduction on what you can do with silicon and germanium, and later also we will add another material, which is tin. So the first application I would like to present is the possibility of looking beyond our bare eye, so looking in the infrared. I would like to make two examples. One is the case of a germanium-silicon heterojunction, and the second is the case of a germanium-tin alloy. So first of all, what it is an heterojunction. So an heterojunction is a junction between two different semiconductors. So we have seen that semiconductors are characterized by band gap. So I have a larger gap, Eg1, and smaller gap, Eg2. There are different ways how this interface phenomena of forming an heterojunction can go. So the nomenclature is not very imaginative. They're called type 1, type 2, and type 3. So in type 1, what happens is that electron and holes are all on the same side. In type 2, electrons are on one side and holes on the other. And in type 3, actually, we have that the valence band of one semiconductor is in contact with the conduction band of semiconductor. So for the point of view of application, most relevant cases are this one, type 1 and type 2. Actually, this technology of using heterojunction, I mean, one of the first applications, at least to my knowledge, is what so-called multi-junction solar cell, which are the solar cells which typically have 28% efficiency, which are used on satellites. These solar cells are putting together 3-5 semiconductors with different band gaps. So you start with one with a wider gap, which takes, let's say, the visible part of light at shorter wavelength, but it cannot absorb, let's say, the one at longer wavelength, the yellow one. Then you put another semiconductor with a smaller band gap, which will take this part, and then another one which takes the infrared part. And so in this way, you generate electron-hole pairs, which can be collected and will give you the output power of a solar cell. And if you compare this with the case of silicon before, so again, we have here the solar spectrum, and this is a part of power that I can take out from the cell, so the efficiency of the cell itself. And you see that using a multi-junction approach, I can actually cover more and more part of the visible spectrum. So if there is an interesting paper where you can make a calculation that if you make, like, I think, 72 heterojunction, you will get to the 94% efficiency, which is not far from the Carnot limit for a solar cell. So inspired by this approach of using different material for absorbing different part of the light spectrum, we actually thought to use this idea not to make a solar cell, but to make a photodetector. So we are not interested in generating power, but we are interested in reading some light signal. So what we did, we put on top of the other silicon and pure germanium. So now you should know these are the defects required to relax the germanium. And we have seen that these two materials have very different absorption properties. So if I shine a mixture of visible and infrared light, I will add that the visible light will be absorbed in the silicon, and the infrared light will be absorbed in the germanium. To actually get some photocurrent, some signal out of this device, you need some additional steps. So you need to actually make a p-n junction here and a p-n junction here. And in this way, you essentially form a device where you have two diodes, one opposite to the other, in a back-to-back configuration. And this means that if you apply, for example, a positive bias to the system, you will have a photocurrent coming only from silicon. And so the photocurrent will look like this. will be something going from to 400 nanometer to 1200 nanometer, okay, which is basically, this limit is the energy gap of silicon. If you instead use a negative bias, you will have light absorbed in the germanium part, and so you will only see the infrared part with a small overlap. So this means that with a single pixel, which is how this structure here, you can actually take two images. So one with a positive bias, where you see the visible light of your system, and one with the infrared part, which our eyes cannot catch, but you will have it exactly superposed one on top of the other. So using this device, we did, for example, this set of experiments in our lab. So we don't have, let's say, a very high resolution. So you can see this is a blue bottle imaged with a mobile phone silicon camera. So it's very nice. And this is what the same image taken with our sensor, which is the pixel size is much larger, okay? And so, but basically the information content is the same. This is a blue bottle. Now, when you reverse a bias and you take the same image and you look at the infrared, what you see is that exactly this plastic is transparent, as many polymeric plastics, and water, the water inside the bottle, is actually a strong absorber in the infrared. So you can look inside the bottle and tell that it's empty or filled up. Another experiment is here. So here you have a series of other small bottles filled with different substances, isopropanol, ethanol, water. This is empty acetone, and this is a mixture of isopropanol and water. They all look transparent in the visible light. So this is actually one of the reasons we cannot bring water bottle on airplanes, because there is no way of telling quickly if it's water of acetone, for example. And if we use our detector in the visible, we have the same kind of information, so they all look the same, more or less. But again, if we switch on the infrared light, we see that now these bottles have different colors, and actually you can train a classifier and to distinguish what is what in this bottle. And this is using essentially just, let's say, the positive or negative bias. You can go even farther, because we can continuously change the bias. So we can go from positive to negatives in how many steps we want. So this is done every like 5 millielectron volt. And so you have a continuous variation of responsivity of photocurrent. And so what you can do is you can actually use this and scan not the wavelength, but the bias. And you obtain these different curves for the different bottles that we have seen. But you see that we have some spectral information inside. So each bottle has a distinctive curve, especially this minimum here is different for every substance we are analyzing. So again, we can think about training some classificator to understand what we have in the bottle. So we see that all this structure, the absorption is limited to the band gap of germanium, which is the direct band gap of germanium, which is around 1550 nanometer. It would be actually nice to go farther in the infrared. And again, we can exploit another possibility offered by semiconductor, which is micro and nano structuring, to do this and move farther in the infrared. So what we did a few years ago was actually changing the substrate. So we don't grow anymore on a flat silicon substrate that you buy from a supplier. But before performing the growth, you can do this deep etching. So you can carve this pillar, which are typically 10 micron tall and a few micrometers wide. And you can do this in a very large area. And again, this is something that is done very easily with silicon. With other materials, would be very difficult to obtain. What happens when you put germanium again on top of this is that on each of these pillar, you nucleate a crystal. We call it microcrystal. And you see that they are very regular with nice facets. And actually, depending on the spacing and dimension of the pillar, you can have different morphologies. So you can have pillars which are relatively flat, or microcrystal which are relatively flat, and other which are faceted like this one. And actually, so we spent a few years studying the physical properties of this kind of system, but since we are in engineering school, so we also like application. So we said, okay, is there something useful we can do with this? And one possibility was this one, actually. If you have an inclined facet and a high refractive index material like germanium or silicon, when light comes and hits this inclined facet, it will be trapped inside. While if it comes on a flat part, it will go straight through your layer. So it's clear that now the optical path, and so the possibility of being absorbed for a photon, it's much higher in this case than in the other. So we can expect that if I calculate the absorption of a faceted crystal over one of a flat area, I would get a larger absorption. So we did this properly with solving essentially in a finite difference time domain approach Maxwell equation, and we compared two systems. So one is a flat germanium layer, let's say 5 micrometer thick, and the other one is this faceted microcrystal, which is also 5 micrometer thick. So the amount of absorbing material is the same. It's only the morphology which is changing. And here, these are the two absorption we get from the microcrystal and from the epilayer. And you see that indeed the microcrystal has a larger absorbance. And if you make the ratio, this, which is this green area here, essentially you have stronger enhance in the infrared than in the let's say, shorter wavelength part. So we decided to make a device out of this. Now this comes, let's say, the difficult part, because this pillar, as you have seen from previous image, are all separated one from the other, so it's not easy to make a contact. So we asked our colleague working on graphene, and we actually managed to put a graphene layer on top of this microcrystal. So this is a cartoon. This is how the system looks like before graphene transfer. And these are two examples. So the first one, very bad, no graphene, just some small parts broken. Essentially, the problem here is that since the spacing between this crystal is very small, we have extremely strong capillarity forces. So the strongest material on Earth, as graphene people like to say, breaks due to these capillary forces. And so actually, Virginia, the PhD student who did this, spent a lot of time in the clean room to actually manage to find a way to obtain a continuous layer. And there you can really see graphene like a curtain on this microcrystal. So now we can make measurements, and we can compare the flat device obtained exactly in the same way, so also with graphene, and different morphologies. And if we compare this all together, we see essentially that this was the calculated absorption that I was showing you before, where we expect an enhancement of the absorption. And these are the real data, the responsivity data. And again, we see here that in this part, we see a stronger absorption in the infrared where we want it to have it. So we can actually extend the sensitivity of our device by engineering, let's say, the coupling between the incoming light and the absorbing medium, in our case, germanium. So we reach with this approach like 1800 nanometers, but it's actually, if we go from the, say, shortwave infrared to the mid-infrared, which is this range here, there is actually plenty of interesting application, because this is the region, the so-called fingerprint regions, where molecules have their vibrational energy levels. And so you can, if you would be able to detect these substances very easily, you would be able to, for example, to miniaturize or make on a chip sensing element for environmental control, hazards, brief analysis, and so on. There is also this very interesting wavelength here where there is no absorption for the atmosphere, which can be used for telecommunication, free space telecommunication. And so we wanted actually to move further in this plot to make possible all these applications. And so we need a material absorbing even more in the infrared. So germanium is no longer good. So we go down one step in the periodic table, and we find tin. So tin at room temperature is essentially a metal with an hexagonal phase. If you cool it down a bit, it becomes also a diamond-like structure, similar to germanium. And so we can think about mixing these two materials and going from a material like this, which is germanium, where all the electrons are, which is an indirect material, so very little absorbing, to a material like this, which is direct and has a smaller band gap. Now the issue is that germanium tin is not as forgiving as silicon germanium. So if we look again at the phase diagram, so here you have a full phase diagram between pure germanium and pure tin. This is just a zoom of the first 1%. Essentially, we can obtain an alloy of silicon on germanium and tin, only for a few, like 0.5% germanium tin content, which is not useful for anything. If you go above this limit, in this region, what you obtain is two different phases. So you will have germanium and droplets of metallic tin forming. So it's no longer a material which can be used for fabricating optoelectronics or microelectronic devices. So actually, only very recently, the technology evolved in such a way that this material can be realized. So this is an example of a collaboration we had with the Forschungszentrum in Jülich, and we repeated the same dual band thing, this time with germanium and germanium tin. So you see the quality of this epitaxial germanium, and again, we performed the experiment to tell what's in this bottle, which kind of solvent it is. The problem here is that this technique can be performed only on a full wafer. So you have to deposit your germanium tin everywhere. And if you consider the, let's say, processes required to obtain a device, epitaxy is very typically the first step. So the first thing you do is deposit your germanium tin layer. Now the problem is that if you then have to heat up your system, for example, for making contacts or for any other process, you will get back to this situation. So thermodynamics will claim its place, and you will again form tin. So the idea is that can we move this process of forming germanium tin later in the fabrication and have it only where we need it? So if I need just a few square micrometer of germanium tin, can I make it locally? And so for doing this, we are actually working together with the team here of Enrico Napolitani. And the technique we use is pulse laser melting. So again, if we want to trick thermodynamic and not fall into the equilibrium case where we have the two phases separated, we need a process which is very strongly out of equilibrium. And I think this is really the case with pulse laser melting, because what happens in this kind of technique is that, for example, you start with germanium, you sputter on top a metallic layer of tin, so this would be an amorphous material, and then you heat it hard with a laser, which melts the first few hundreds nanometer of your system, so the system is completely molted, and it essentially recrystallizes in a matter of few nanoseconds. So it's a very quick phenomenon which is out of equilibrium. But in this way, you're able to crystallize your system in the phase you want, so in a unique phase of germanium and germanium tin. So these are actually very preliminary result of this. So Enrico and co-workers did a lot of study on the structural properties of the system. I will not discuss here. We'll focus on the, let's say, optoelectronic property we are interested in. And so these are preliminary absorption spectra of layers with germanium tin of different content, and we see that actually the absorption at longer wavelength is increasing and is going to So we are able to see the first step of absorption at longer wavelengths. So in this we are continuing this work, trying to have a thicker germanium thin layer. So we discussed about heterojunction and photodetection. Keeping the focus again on photonics, there are other things you need to do with light. And as an example, I would like to take this paradigm of a photonic on the lab, photonic lab on a chip. And I want to show you how we can actually guide light, propagate light over a circuit in a chip, and how then actually we can confine it, for example, when we want to send something. So the idea is that the operation that you typically do in a several square meter lab can be done on a chip that can take favor of the infrastructure built up for a semiconductor, so being fabricated in the same fab where CMOS transistors are done. So this chip would contain typically photodetectors, we already seen it, but also some way to make light traveling and some places where light can interact with the external world and sense something. So I will start by discussing the waveguide problem and then focus more on these sensors, how we want to do it, again, using heterostructure. So this is a schematic representation of a waveguide. So what we need, as I was telling you before, it's a contrast index. So we need a low refractive index material and a high refractive index material on top where we can carve our ridge waveguide. So the most popular case of this technology is a so-called silicon photonics, where we have an oxide layer as a low refractive index medium and a silicon, crystalline silicon as a high refractive index medium. And so this is essentially technology which is used in telecommunication. But we are interested in sensing, so we want to move at wavelengths which are not 1300 nanometers, but actually microns. And so to do this, we exploited a different approach, and the two materials are now silicon and germanium. So I was telling you before that germanium has a high refractive index than silicon. So if I make a structure like this, I start from silicon, I again increase slowly germanium until I have a very high germanium content here. My optical mode will try to be confined in the upper part, okay? And so here you see the grading on the composition will correspond to a grading in the refractive index. And this grading actually adds one more degree of freedom in designing your waveguide. So in silicon photonics, you have two materials, silicon and silicon oxide. And so everything comes out of, let's say, the fabrication step. Here, we have an additional possibility of changing the refractive index as we grow our structure. So this then can be combined with fabrication. So with this, you can then do, I've taken a few examples. This is a work that we are carrying out with the C2N Center in Paris. And this is a ring resonator made of silicon germanium, so light can be trapped here. And this is an array of different interferometers where you can make interferometry on a chip scale. So since our focus today is on sensing, I would also like to show you a sensing experiment. So these are spirals of waveguide. So it's a way to actually put in on a small footprint, a few hundreds of micrometer footprint, millimeters of waveguide. And on top of this waveguide, you can put something to sense. In our case, this is simply photoresist, is a polymer which is coating our spiral. So now if I make the transmission spectrum of the clean waveguide and of the polymer-coated waveguide, you see that we have some differences. And these differences actually corresponds to the absorption of this polymer induced by the presence of a polymer on top of a waveguide. And so, of course, the longer is the waveguide, the more you see the effect. And so this is the first example of sensing experiment. But here we still need quite a lot of material. So our sample, let's say we want to make blood analysis, needs still to be sizable because we need to cover an area which is millimeter size. So can we actually go farther and confine light in a smaller spot and so measure a few molecules? This is possible if I use antennas. So an antenna, we know it from, we see in our roofs, is essentially one or more conductors which are placed one close to the other in such a way that light can be confined in a small region. It's actually, in this case, is a nanometer region. So this is a diagram where we see one of the optical mode of the system. So we see a strong electric field confinement here. And this is the actual fabrication done by our colleagues in Glasgow. And so again, I want to stress that this kind of almost perfect fabrication, you can have it only in semiconductors. There are no other simple tools to do it with a metal or whatever material. You can make it on a large area with a very high reproducibility. So this is a zoom on this, of these arrays of nano antennas from the top. So you see that the gap is only 300 nanometer. Actually, to have this antenna to operate, so shape is important, but also the electronic properties of the materials are important. So it's actually important to work close to the plasma frequency of the material itself. So what it is, the plasma frequency? So what you see here is the reflectance of gold. So we can distinguish two main regions. One where we have a very high reflectance, which is essentially where gold is metallic, has a metallic behavior, so it's highly reflective as we see it with our bare eye. And one where gold is transparent, and so it behaves more like an insulating material. So the transition between these two behaviors is set by the plasma frequency, which more or less corresponds to this point here. You can make a very simple free oscillator model and get the value of the plasma frequency, and we see that this depends on the density of the carrier you have in your system. So for gold, this density is fixed. So it's roughly 6×10⁻22 per cubic centimeter. So you cannot change it. So gold will work nicely only in this visible range. If you try to obtain the same properties in the infrared, which is where we want to go, you will fail. But now let's say if we use a semiconductor, what will happen? So this is the case of germanium with a relatively low doping. We see again the metallic behavior. Now you see the scale is completely different. These are microns. We see the insulating behavior. The trace is this interference fringes that you typically have in transparent media. And again, we have this plasma frequency. But now this number, n, can be tuned because in semiconductor, we can tune the doping level. So we can go from 10⁻17 to 10⁻20. And so adapt my material to the purpose I want to achieve, which is sensing in the mid-infrared. So this is what we did. So these are different samples with increasing doping level, going from a few 10⁻18 to a few 10⁻19. And then this doping was done in our deposition tool, adding phosphorus during growth. But then we noticed that adding more and more phosphorus was not giving any actually further shift. So we could not get away from this 10 micron plasma frequency. And the reason, again, we discovered, thanks to the collaboration with Enrico, comparing Hall effect and secondary ion mass spectrometry. So the Hall effect will tell us the active carrier, so the one which are really free to move and participate to plasma frequency, while the SIMS will give us the chemical composition, so how many phosphorus atoms I have in my system. So many of them, we found out, were not in the right place or were not activated. So we have much more phosphorus atoms than electron in our system. So again, we need something to, say, improve our material. Actually, this limit is actually a fundamental limit of this system given by the formation of clusters between phosphorus and vacancies. And so again, we need something to shock our system and go outside what equilibrium will tell us, which is you cannot go above a few 10 to the 19 during epitaxial growth. So again, we relied on pulse laser melting. So here you see a set of samples where we have, again, Hall effect and seams, this time as a function of temperature. So again, if we go down in temperature, we see that we can incorporate much more phosphorus, so we can go up to 10 to the 20. And then, but again, we see that actually the conductivity is very poor. Only, let's say, 1 out of 100, or actually 1 out of 1,000,000 of 1,000 of these atoms are actually activated. But again, if we shock our system and let it melt and then recrystallize in a few nanoseconds, the phosphorus will get in the right place, and we can actually have a jump in the plasma frequency and cover all this range. So this is the first attempt where we didn't achieve full activation. I think it was like 80% or so. And then we improved our process. And so again, we can now span in a broad range of the mid-infrared, changing the material. And so design and use nano antennas for a specific purpose. One example of how it works. So we try to sense this chemical substance, which is called CEMS. It's a simulant of an explosive material, but it's not explosive, so we can use it in our lab without having the police around. And typically, you can analyze this system with the Fourier transform interferometer, which is a benchtop tool. I guess you have many also in your department. And so if you take the transmission spectra, you will see some distinctive lines, which are the absorbing lines of this substance. So we want to do this on a chip, not using the Fourier interferometer. So we fabricated an array of antennas. We covered it with this substance. And we actually took in reflection geometry, the differential reflection between the chip with the explosive simulant and without. So these two curves looked pretty much similar. But if you take the difference, you recover a spectrum where, for example, here, around 700 inverse centimeter, you see exactly the same peak. It's less effective at longer, higher wave numbers because, I mean, this kind of, this resonance is the resonance we have in this kind of structure are also quite sharp from the point of view of, let's say, spectral density. So if you want to detect at another wavelength, you need to slightly change the geometry of your system. But this proves essentially that you can have all using silicon and germanium, you can use the possibility offered by semiconductor technology, formation of heterojunctions, nanofabrication, and doping to actually tailor your material system for a specific application. So as a last topic, something which is kind of very different from what I presented so far, but it has become very, very popular in the past 3-4 years. So all the people working on germanium epitaxy are now excited by the possibility of using germanium Hall states, so in the valence band, to form spin qubits. So it's something a bit unrelated to the rest, but essentially this again gives the idea of how many things you can actually do with a single material system. So briefly, what it is a spin qubit? Spin qubit is a qubit in general is essentially a quantum system with 2 levels, 2 states that can be mapped on a Bloch sphere. So where essentially these 2 components are the 2 angles here that defines the composition that is a generic state as a function of these 2 eigenstates, 0 and 1. So for example, fundamental state 0 on the Bloch sphere would be mapped like this. Its orthogonal state will be the reverse one, and it will be this one. And if you form some combined state, you will have, for example, for the X plus this combination, and for the Y plus this combination. So essentially so this is a two-level system, but the Hilbert space can be fully described by these two single wave functions. So you can describe any state you want on this block sphere by properly combining with this complex coefficient, the state 0 and 1. So once you have this two-level system and you want to do logic with it, you want to do computation. Computation means that essentially you need to have a starting point, which is reproducible. You can put your place state in a system, and then apply some operation, which in logics are called gate. So this is the Hammer gate, which takes this state and brings it here. And then we have the Z gate that takes these states and brings it there. And again, an Hammer space, which brings it down again. So with these three elements, basically, you can build up any kind of logic operation you want. So this is on paper. This is interesting from the point of view of textbook quantum mechanics. How do we do it in reality? So we need to find a quantum system with two levels, which maintains the coherence for a time long enough that I can do this operation, and find physical means, external stimuli, like a magnetic field or a microwave pulse or whatever, that corresponds to this different logic operation. So nowadays, there are few platforms which are being considered. So the most popular one is using superconducting circuits. So the IBM quantum computer, which you can access online, you can write program and have problem solved, is actually of this kind. I think now we are around 60 qubits. Other possibilities are color centers, for example, in diamond. You have also cold ions as a quantum system where you can have two levels and do quantum computation. And also, even though they are much debated now, topologically protected system like Majorana fermions. What I would like to focus on today is actually quantum dots, because this is a material system, a quantum mechanical system which can be implemented in semiconductors. So nowadays, I said, superconducting qubits, they reach around 60. I think the best value for, let's say, semiconductor quantum dots is around 12 or 15, so we are a bit back, let's say. But the idea is that already nowadays at Intel or at the TSMC in Taiwan, they produce objects which are nanometer scale. So the possibility would be to transfer also not only classical computation, but quantum computation on the same material platform, which is semiconductor, and maybe adding both of them on the same platform. So how do we create a qubit in this case? So here the idea is isolating a single electron and using the charge, or more often the spin, as a two-level system. So how do you confine a single electron in a semiconductor? So you typically, in our case, for the case of germanium holes, you start with the germanium quantum well. So here we have a confining potential where we can confine both electron and holes. And we apply a gate, which is called the plunger gate, which essentially confines holes in our quantum well. So here we will have, at this stage, a two-dimensional system filled with holes. And these holes are in a very high purity material, which is a semiconductor. Now I add other electrodes. In this case, I have two. So let's say that now this is all positive. These electrodes will repel holes and form a small pocket where I can confine just a few electrons. And actually, I can confine only one, or a few holes, I should say, in this case. So one of the simplest way to describe this confining potential is using the harmonic oscillator example. Okay? So we imagine that our electrodes design inside the germanium quantum well a parabolic profile, like the one you have from a spring. So this will be the potential energy. And so this potential is actually moving the system from 2D to 0D. So because it will be mean, it's difficult to plot it on a page, but essentially it would be a three-dimensional confinement. So all the carriers are trapped there. So if we look at the simple oscillator, we know that we have equally spaced level. Finito, sì. Equally spaced level, and the spacing between this level depends on the effective mass. So if I have a very small mass, it means that I can have a very little level, and so I can also go to the level where I have one electron. And this is one of the properties of germanium. So thanks to the very small hole gas, or all effective mass, I can have only one hole in my system. Other requirements is that I have the nuclei are spinless, so this is isotopical composition of germanium. Only one isotope has a spin, which can interfere with the spin of the electron. You can induce superconductivity in germanium much easier than in silicon, for example, using niobium or aluminum contact. And again, you can have a very advanced manufacturing. This is a paper from last year, and essentially this device, I think it was 8 qubits, were made by Intel using their conventional fabrication processes. So with this, I think this is how a laboratory device looks like, and just brief overview of the state of the art in this system. So germanium has been used in the form of nanowire, hot clusters, and also quantum well. And so to conclude, I go back to the past. So germanium was actually the first material predicted by Mendeleev and then found. This is so I started with the periodic table. This is again the periodic table transposed, because we see the elements are in this order, and this is germanium, which was missing at the time. We discovered a few years later. It was also the first material used for making a transistor, and maybe it will be again a first material to bring to large scale quantum computing. So, of course, I'm here speaking, but a lot of people did this work. So my co-worker at Politecnico and people from the other institution. And of course, we need economic support from different projects, which are listed here. Thank you. And maybe I was a bit too long.
Thank you very much. Thank you very much for this general overview, this wide range of applications for this methodology. So I guess there are some questions, quick questions. Any questions? Yep.
On this last part, just a curiosity. With silicon, it is really impossible to do something like that, or? Actually,
so this was done with silicon, this first attempt. The thing here is that in silicon, we have a huge problem, which is that so this is done with electrons in silicon. So we have the 6 valleys of silicon, which are degenerate. So it's very difficult to break this degeneracy and have only one electron placed in one position in space and in reciprocal space. With germanium, since we can use holes, we don't have this degeneracy, and so this is far easier, let's say. Okay, so this is the main advantage, and the other is that actually from the point of view of interaction between electron spin and the nuclear spin, the silicon is a bit more complicated to, you have more isotopes which are not purified, even though this, it can be obtained purified. But I would say the main problem is let's say, degeneracy and also the effective mass, which is not very small, and so you need to make very small device if you want them to work.
It is just another curiosity about, I was really impressed by the phase separation of a droplet, of a selenium droplet, okay, in the alloys. And I was wondering, how stable are they? Do you see any evidence of something like coalescence or?
Of a droplet?
Yeah.
I would say, yeah, I mean, there are also very nice videos, SCM videos in real times, where essentially they take germanium tin, heat it up, and you can see this droplet forming and going around and coalescing one with the other. So it's typically something we consider, I mean, we don't want to see in our material, but I think the answer is that yes, it happens. I don't know if it has been a matter of study, but because the main idea is having an homogeneous, let's say, alloy. But I mean, once the droplet is formed, it's liquid, and so it goes around and tries to increase the volume.
Thank you.
Wonderful talk, really. A very historical description of germanium. So I want to go back to the quantum qubits, and in the scheme that you showed, there is, of course, a dependence on the temperature. So my question is, how much is stable that holds in terms of single holes, in terms of qubit behavior? And make it practical, is enough of a nitrogen, liquid nitrogen temperature, you would go to liquid helium?
It's millikelvin.
Millikelvin.
All this, I mean, all the semiconductor qubits. So this history started with gallium arsenide, and then it moved to silicon, and now it's the time of germanium. But they all work at millikelvin temperature, because and with this you need to reach microseconds coherence time where you can perform the operation.
Are there any chance to make the qubit more stable?
At higher temperature.
At higher temperature?
I would say no, because I mean, I mean, all these quantum states are very fragile, and I think it's. I mean, I don't see any other possibility than having a cryostat. There is also now. So one thing I mentioned, which was coupling with, I mean, proximity effect for superconductivity. Since it's also very difficult to get many qubits entangled in a semiconductor, because every small, I mean, in the community they say the qubits have individual characters. So if you make one half a micron or let's say a few hundred nanometers away from the other, we will be different and work at two different bias and so on. The idea is having, so if you do it even farther, it will be even worse. The idea is having patches of a few qubits which are connected by superconducting microwave circuits. So to transfer the coherence of the states over a longer distance using this. And so for this application, the fact that you can induce superconductivity in germanium is important.
Giovanni, well, so the germanium sensor technology is growing a lot, at least from a research point of view. And what about industries? Well, I know very well that according to microelectronic industries, the interest in germanium, silicon germanium is growing a lot. But what about photonics and quantum computing, according to your experience? Actually,
So the work I presented on this dual band detector give origin to a startup. So actually the PhD who did the work is now my CEO in a small startup trying to bring this technology to the, let's say, to an industrial level. The point here, I think, is that you have already sensors, typically in indium gallium arsenide, looking in the infrared, which are performing much better than germanium for some fundamental physical reason. However, for example, if you want to put this sensor in a car to look through the fog, the INGAS sensor will cost as the car itself. So it's something which is not affordable. So there are applications where one can trade, let's say, worse performances, but for a smaller price, lower price, and enable some applications. So now there are a few companies working in, and also big foundries like Tower Semiconductors, which are trying to bring germanium to the imaging industry. It is already in telecom. So Intel and other players, they do sell photonic circuits where the germanium is used as a photodetector, but in a waveguide configuration. So this is something you can essentially buy from many foundries around. For imaging, it's starting now, I would say.
Other questions?
Thank you. I just wanted to ask, it has been widely said that this year's Nobel Prize for Physics will help us in the study of semiconductors, but how will it work in practice?
Okay, I can answer because actually I have a few colleagues in my department which are working on attosecond, and what they are studying now is essentially the dynamics of intra-band recombination, so happening inside a single band because they happen at this very short time scale. And so these are, I think we will have practical application for high energy or particle detection because, let's say, these attoseconds, they last one pulse. And since they need to be short, eventually you need to have a very short wavelength and so very high energy. So you cannot generate attosecond pulses in the mid-infrared. Typically they work around 15, 20 electron volt and so on. And so you only have accessible some phenomena, which are the one at high energy. So what the people is working on now is understanding this attosecond reconfiguration of electrons in semiconductor, for example, or in gases. So this is, then of course there is always overselling about Nobel Prizes. I think it's beautiful physics. I mean, we don't ask the same for the Higgs boson, or which is the use. It's knowledge. I mean, then sometimes this knowledge turns out in a big revolution like the transistor, some other not. But in my opinion, this is not the role of the Nobel Prize to see what will be the relevant technology. It's for sure an amazing achievement to be able to control a phenomenon. I mean, it's interesting to know. So the age of the universe is about 10 to the 16 seconds, and this is actually 10 to the minus 16 or lower. So I think it's incredible. But so the only application I know about semiconductor is this one. So I don't think it will enter in our computer. Attosecond, it will have to develop newer devices. But there are phenomena that happens on this scale in semiconductor that is interesting to look at because we like this.
More questions? If not, let's thank Giovanni again. And let's convene for the next colloquium, which will take place in a couple of weeks.